bmls.exe is the program which runs the BML simulator interface version 1.6. The interface is a user-friendly program to launch the simulator, hotspot.exe, with a command line argument, which is a text file, after which no user manual intervention is required. The output file naming conventions are discussed now. First, the first two digits are the dimension of the simulated spot cube in terms of number of spots. The next character in the output file name is the run mode. Here, V indicates vacuum mode, which is box mode, and rand mode off. In vacuum mode, bits exiting the simulated volume are simply lost, resulting in a decreased bit density until no more particle motion or radiation occurs and there are 0 bits leaving the simulated volume, and that's, of course, absolute 0 Kelvin state. If we start with RAND mode on, we have R in the output file name. RAND mode, bits exiting the simulated volume are replaced randomly on all 6 sides by injecting a sufficient number of bits into the simulated space in each tick to achieve the bit density specified at the beginning. You might think of RAND mode as embedding the simulated space in a much larger volume with similar bit density and at thermal equilibrium, more or less, with the simulated volume. If we have both checked, we have S indicated, and if we have just the box mode check, where exiting bits are reflected back into the simulated space, is indicated with a B. Now, if we change the bit density and press enter, ta-da, we get that coded in 4 digits here in the output file name. Next comes the bit operations order, which can be changed. There's a different bit operations order, and it appears in the file name, so we know what bit operations order was used in the simulation. The SUV bit operations order, scalar, unconditional, vector, and F for strong, is the one and only bit operation order which appears to be physically correct. If you change the order, they don't commute and you get different results. Okay. Lastly, the trial number. Here's trial number 2, trial number 3, and so forth. Now, the random seed, if it's a non-zero value with the same simulated dimension and bit density and other parameters, you're going to repeat exactly the same random seeding that you had before with that particular random seed. With 0, everything is just randomized right from the beginning. Now, the display or look mask typically has both M bits and L bits checked for display, and we start out in X-ray mode. If that's unclicked, we have what's called solid mode. You notice the file name is not changing because this doesn't affect the data actually saved to file while the simulator is running. In plane mode, we're showing an XY plane at some Z dimension depth in the simulated space. If neither one is checked, we're showing a solid view. Basically, if there's a lot of bits in there, we're going to see the near surface of the spot cube represented in the display. So we normally would start with an X-ray view. Now, we want to set the initial state. When we set the initial state, of course, the bit density is an important parameter. If the radius is non-zero, it means that the point defined by x0, x1, y0, y1 ranges, if they're all set to an equal number, the 0 and 1 part for x, and the same for y is 0, that would be the center of a sphere of the radius shown here in terms of the spot dimension to seed random bits. Normally, I'm having this 0 because I'm not making spheres, but like if you want to see a big explosion or something, you create a sphere of bits and watch what happens when you start to run. Okay, now the next row here is your 8 particle types and the labels for them. These are the 8-spot types. If checked, it means that the random seeding to set an initial state will include these particles. Any ones that are unchecked will not be seeded. The next row is the type of bit, and the M bits have a positive or a negative charge, so we can select, let's say, let's just use positive bits, or let's just use negative ones, or in this case, let's use both. Here we're setting the direction of the L bits, which ones we're going to use in or allow to be inserted in the initial state, and in this case is all types, in the right left, in the X dimension, or up down in the Y dimension, or coming toward us or going away from us in the Z dimension. Now here, what if we wanted to just seed only part of it? We could increase this, let's say, to 16, decrease this to 16, and now we're going to, in the X dimension, only seed this range, and the full range for a dimension 48 space for the Y and the Z dimension. So that's what this is all about. You notice if I change the dimension up here, okay, these are automatically set to include the full range from left to right, top to bottom, and front to back in the Z dimension. Now, there's a few other little things here which we can do to set the experiment number. Like if we set it to 1, that's experiment 1. It showed up here in the file name, and that is your laser experiment. If number of ticks, which are simulator ticks, which are the application of the 4-bit operations in a cycle, SUVF in this case, if that's set to 0, it will sort of run to forever. Now, certain of these experiments will terminate all by themselves when certain criteria are met. Not experiment 1, but certainly experiment 2 will. Or we could set a certain number of ticks that we want to run. Let's put 400. All right, let's make it 4,000. Actually, we could do this after we set the initial state. Once we have set our parameters here, we can save. So this is our first run. Now, what if we wanted to repeat that run, but add an electric field, let's say? This is going to, so there we're going to have this data, same deal, and let's make it experiment 0. Okay, so we're going to take that off. And we're then going to, only in the upper part of the Y dimension, so we're going to take this down to 0, or let's take it to -1. So including the full span of the X dimension and the full span of the Z dimension, but only in the upper part of the simulated cube that we're going to see, we're going to add in all particle types, let's say, some nits, which are going to be the negatively charged M bits, and that's the only kind of bit we're going to add. All right, set initial state. So we're adding more stuff here. In other words, you can keep adding things forever, basically, in your setup for an experiment or a run of the simulator. Now, when I click Save Parameters again, we've got the 2 files. Now, we've got 2 runs. You've seen that we can create as many of these files as we want. It could be that we want to run the simulator overnight while we're sleeping or going out and visiting with friends, and it's all going to be automated and run all by itself, requiring no further manual input. Now, when I click Run Simulator, what's going to happen is that this window of the interface will be hidden from your screen. The simulator will be launched using this text file here, which is located, by the way, in your bat subdirectory, if you want to look at it and edit it or whatever, as the first command line argument. When hotspot executed is launched with such an argument, it automatically modifies its behavior in several different ways so that no manual input should be required. So that means when it finishes job 1, you might say, this window will appear again and the interface will launch job 2. And we only have 2 jobs listed here, but we can have really as many as we want. Okay, that completes our introduction to the Binary Mechanics Lab Simulator interface. Thank you for your attention. Good night.